Welcome to this walkthrough of LeetCode problem number 254, factor combinations. In this problem, we'll explore how to generate all unique combinations of factors for a given integer. This is an excellent exercise in recursion and backtracking, so let's dive in. In this problem, we are tasked with finding all the unique combinations of factors of a given integer n. Factors are numbers that divide n evenly, meaning without leaving a remainder. Here, we specifically exclude 1 and n itself as valid factors, so the focus is only on the numbers in between. For example, if n is 12, valid factors would include numbers like 2, 3, 4, and 6. Each combination of factors should be represented as a list, such that when all the numbers in that list are multiplied together, the product equals n. Moreover, the numbers in each combination must be in ascending order, and duplicate combinations are not allowed. The input is a single integer n, which can range from 1 to 10 million. The output is a list of lists, where each inner list represents one unique factor combination. If no valid combinations exist, the output should simply be an empty list. Let's look at an example with n equals 12. If we factorize 12, we find that it can be expressed as 2 multiplied by 6, or 3 multiplied by 4, and it can also be broken down further into 2 multiplied by 2 multiplied by 3. These combinations are valid because all the numbers in each list are greater than 1, less than 12, and, most importantly, their product equals 12. Additionally, the numbers in each combination are sorted in ascending order. The output for this input would therefore be 2, 6, 3, 4, 2, 2, 3. Now, consider a different example where n equals 37. Since 37 is a prime number, it cannot be factored into any numbers other than 1 and itself. Because the problem excludes 1 and n as valid factors, there are no valid factor combinations for this case. The output here would simply be an empty list. For another example, take n equals 16. When we factorize 16, we find multiple valid combinations. It can be expressed as 2 multiplied by 8, or 4 multiplied by 4, or broken down further into 2 multiplied by 2 multiplied by 4, and even as 2 multiplied by itself 4 times. These combinations are valid because they meet all the criteria. The numbers are greater than 1, less than 16, the product equals 16, and the numbers in each combination are sorted in ascending order. The output for this input would therefore be 2, 8, 4, 4, 2, 2, 4, 2, 2, 2, 2. This demonstrates how the problem handles cases where the input is a perfect power of a smaller number, ensuring that all valid combinations are included. To summarize the constraints and edge cases, first, the value of n will always be between 1 and 10 million. The factors considered must be strictly greater than 1 and less than n. The numbers in each combination must appear in non-decreasing order, and duplicate combinations are not allowed. For edge cases, if n is a prime number, the output will be an empty list since there are no valid factors. Similarly, if n is very small, like n equals 2, the result is also an empty list because no factors other than 1 and n exist. On the other hand, when n is a perfect power, such as 16, the output must include all possible combinations, including cases like 2, 8, 4, 4, and 2, 2, 4. These considerations ensure that the solution captures all valid combinations while adhering to the constraints. To tackle the factor combinations problem, we aim to generate all unique combinations of factors for a given number n. The difficulty lies in maintaining ascending order in the combinations while avoiding duplicates. Let's start by examining a few potential approaches. The brute force approach is straightforward but inefficient. The idea is to iterate through all possible combinations of numbers between 2 and n1 and check if their product equals n. This can be implemented using nested loops, but it has exponential time complexity because of the sheer number of combinations to check, especially for larger values of n. This method doesn't leverage the inherent structure of factors, like their recursive nature, so it's not ideal. On the other hand, the recursive backtracking approach is much more promising. Here, we use the observation that factors can be broken down recursively. For instance, if a factor a divides n, the quotient n/a can also be decomposed into factors. By limiting our search to factors up to the square root of n and ensuring combinations are built in ascending order, we can avoid duplicates while systematically exploring all valid possibilities. In the recursive backtracking approach, we begin with an empty combination and build it incrementally. At each recursive step, we iterate through potential factors starting from the current factor to maintain ascending order. If a factor divides n, we add it to the combination and recursively calculate combinations for the quotient. Once we've explored deeper paths, we backtrack by removing the last added factor, which allows us to explore alternative paths. The time complexity of this approach is approximately O(k) per valid combination, where k represents the depth of recursion. The total number of combinations depends on the prime factorization of n, which makes this method adaptive to the structure of the input. This approach is particularly favorable because it avoids duplicates, directly leverages the problem's recursive structure, and is computationally efficient compared to brute force. Based on these advantages, the recursive backtracking approach is the optimal strategy for solving this problem. The optimized recursive backtracking strategy works as follows. We define a helper function that takes the current number n, a starting factor, and the current combination of factors. For each recursive call, we iterate through potential factors from the starting factor up to the square root of n. If a factor is valid, meaning it divides n, we add it to the current combination and recursively explore the quotient. After the recursive call completes, we backtrack by removing the last factor to explore other possibilities. The pseudocode implementation captures this process, starting with the backtrack function and initializing an empty result list. This approach strikes a good balance between efficiency and clarity. It avoids duplicates by ensuring factors are added in ascending order and skips unnecessary computations by only considering valid factors. The trade-offs are minimal, with the primary consideration being careful implementation to avoid redundant calls. Overall, this strategy is elegant, scalable, and well-suited for generating all unique factor combinations of n. To solve the factor combinations problem, we use a backtracking approach to systematically generate all unique combinations of factors for a given integer. The first step is to define a backtracking function. This function will operate recursively, exploring all potential factor combinations by breaking the problem into smaller subproblems. It takes three inputs: a list called current to store the ongoing combination of factors, a starting point start to ensure factors are added in ascending order, and target, which represents the remaining product we need to factorize. The recursion's base case occurs when target equals 1. At this point, if the current list contains factors, they form a valid combination, and we can store it. The next step in the algorithm is iterating through potential factors, starting from start and going up to the square root of the target. This range is sufficient because factors repeat beyond the square root. For each factor I, we check if it divides target evenly. If it does, I is a valid factor. We then append I to current and make a recursive call to continue factorizing the reduced target. Once we've made the recursive call to explore deeper combinations, it's time to backtrack. This process involves removing the last added factor from the current list, effectively undoing the last step and allowing us to try other possibilities. This ensures that we systematically explore all valid combinations. Additionally, for every valid combination of factors identified during the recursive exploration, we append it to the result list before backtracking. This guarantees that all unique combinations are captured. After all recursive calls are complete, the result list containing all valid groupings is returned. Some key insights into this algorithm include the importance of maintaining ascending order by starting the iteration from the last used factor. This prevents duplicates such as 2, 3, and 3, 2. Another optimization is early pruning, where we iterate only up to the square root of target, significantly reducing the number of checks needed. Lastly, the recursive depth is proportional to the number of factors. Each recursive step splits the target further, making the algorithm efficient for large numbers with many factors. To implement this algorithm, we rely on a few key data structures and operations. The result list stores all unique combinations of factors, while the current list keeps track of the ongoing combination being explored at any given moment. The divisibility check is a crucial operation, as it determines whether a number is a valid factor of the target. This is done using the modulo operation, target %I == 0. Recursive exploration is the mechanism that allows us to delve deeper into the factorization tree, systematically reducing the target and finding new combinations. Backtracking plays a critical role here, as it ensures we explore all possible paths without missing any combinations. Once a path is explored, we remove the last factor from current to try other possibilities. The provided Python implementation demonstrates these concepts in action. The backtracking function checks the base case where the target becomes 1 and ensures only non-trivial combinations are added to the result list. For each valid factor, it appends the factor, makes the recursive call, and then backtracks by removing the factor. Finally, we handle the edge case for the full factorization. If the remaining target is greater than or equal to the starting factor, it means target itself can be treated as a factor. In this case, we append target to the current combination, add the combination to the result list, and then backtrack by removing target. This ensures completeness in capturing all factor groupings. The time complexity of this algorithm depends on the number of valid factorizations of the input n. In the worst case, such as when n is a power of 2, the recursion depth is proportional to the number of factors, leading to a complexity that grows with the number of recursive calls. The space complexity is determined by the recursion stack. Since each recursive call splits the target further, the maximum depth of recursion is approximately logarithmic with respect to n, making the space usage efficient. This combination of recursion, backtracking, and mathematical optimizations makes the algorithm both robust and efficient for solving the factor combinations problem. This Python implementation solves LeetCode problem number 254, factor combinations. The goal is to find all unique combinations of factors for a given number n. The solution uses backtracking to systematically explore all valid factor combinations. The getFactors function begins by defining a helper function backtrack, which takes 3 arguments: start, the starting factor to consider, product, the current product of chosen factors, and path, the current list of factors. This recursive function will explore all potential combinations of factors. The base case checks if the product equals n. If it does and the path contains more than one factor, we append a copy of the current path to the result list. This ensures that only valid combinations are included. The for loop iterates over potential factors starting from start up to the square root of n. If the current factor I divides n evenly, it is added to the path, and a recursive call is made to continue exploring further factors. After the recursive call, the last factor is removed from the path to backtrack and explore other possibilities. Additionally, the implementation includes a mechanism to handle the inclusion of n itself as a factor at the initial level. This ensures that combinations like n are considered when appropriate. Finally, the result list accumulates all valid combinations, which is returned as the output of the getFactors function. This approach guarantees all unique combinations of factors are generated efficiently, leveraging backtracking to prune unnecessary computations. Here, we begin the Java implementation for generating all unique factor combinations of a given number n. The main method getFactors serves as the entry point. It initializes an empty list called result to store the valid factor combinations and then calls the helper method backtrack. This helper method is where the recursive logic resides. It begins with a starting factor of 2, a product initialized to 1, the given number n, an empty list called path to track the current combination, and the result list to collect all valid solutions. Within the backtrack method, the base case checks if the product matches n. If so, and if the current path contains more than one element, which confirms it's a valid combination, it adds a copy of the path to the result list. Otherwise, it iterates through potential factors starting from the given start parameter up to the square root of n. This ensures we only consider factors up to where they are needed and avoids redundant checks. For each factor, we first verify that multiplying it with the current product does not exceed n. Then, we check if n is divisible by the factor, ensuring it's a valid candidate. If it is, we add the factor to the path, call backtrack recursively with the updated product and path, and finally remove the factor from the path to backtrack and explore other combinations. The final part of this recursive method handles a special case to ensure completeness. If the current product multiplied by n equals n, which effectively means we are considering n itself as a factor, then we add n to the path, record it as a valid combination by adding a copy of the path to the result list, and then remove n from the path to backtrack properly. This ensures that single factor combinations involving n are included if they meet the criteria. With this, the recursive process can exhaustively generate all unique combinations of factors for the given number while avoiding duplicates or invalid paths. The complete solution is then returned as the result list from the getFactors method. This approach ensures clarity, efficiency, and correctness by leveraging recursion with backtracking and limiting the search space to only valid factor candidates. To solve the problem of finding all unique combinations of factors for n equals 8, we begin by setting up our variables. The result list is initialized as empty, which will eventually store all valid combinations. We also define start as 2, since we exclude 1 and n itself from the combinations. The product starts at 1, and path is an empty list that will keep track of the current factor combination. The process begins with the first recursive call to the backtrack function, where we iterate starting from I equals 2. Since 8% 2 equals 0, we know that 2 is a factor of 8. We add 2 to the path, making it 2, and make another recursive call with updated values. Start remains 2, product becomes 2, and path is 2. This sets the stage for exploring further combinations of factors. At this stage, the product is 2, and we continue iterating with I equals 2. Since multiplying 2 * 2 equals 4 is less than or equal to 8, we append another 2 to the path, resulting in 2, 2. Another recursive call is made with start equals 2, product equals 4, and path equals 2, 2. Now, the product is 4, and we find that multiplying 4 * 2 equals 8 matches our target n. This makes 2, 2, 2 a valid combination. We add this combination to the result list and then backtrack, removing the last factor from path, which now becomes 2, 2. To explore other possibilities, we increment I to 3 at product equals 4. However, since 4 * 3 8, no further combinations are found along this path. Backtracking further to product equals 2, we increment I to 3 and later to 4. When I equals 4, it is valid, and we find the combination 2, 4. After completing all explorations, the result contains 2, 2, 2, 2, 4. When working with n equals 12, we start with the same initial setup as before. Result is an empty list, start is 2, product is 1, and path is empty. We begin iterating from I equals 2. Adding 2 to the path and recursing leads us to multiple valid combinations. For instance, 2, 2, 3 is formed when we repeatedly append 2 and then append 3 to complete the product of 12. Another valid combination is 2, 6, where multiplying 2 * 6 equals 12 directly meets the target. Next, we try I equals 3, or appending 3 to the path and recursing results in combinations like 3, 4. After exploring all possibilities, the final result for n equals 12 is 2, 2, 3, 2, 6, 3, 4. For the edge case where n equals 37, we notice that 37 is a prime number. This means it has no factors other than 1 and itself. Since the problem specifically excludes 1 and n from the factor combinations, there are no valid combinations to return. As a result, the result remains an empty list. The time complexity of the getFactors function hinges on the recursive structure used to generate all valid factor combinations. At the heart of this lies the recursive tree structure, where at each level, we iterate through potential factors ranging from the start value up to the square root of the current number n. In the worst case, the depth of recursion can reach up to log n, because each recursive call reduces n by dividing it by one of its factors. For instance, if n is 16, we can keep dividing by 2, resulting in the combination 2, 2, 2, 2. Additionally, within each recursive call, we explore all possible factor combinations by iterating through the range of factors. The total number of recursive calls is tied to the number of ways n can be expressed as a product of integers, which grows approximately as 2 log n in the worst case. This is because the number of combinations increases exponentially with the logarithm of n. Now, combining the depth of the recursion, which is log n, with the exponential growth in the number of combinations explored at each level, the overall time complexity of the solution is approximately 2 log n in the worst case. This can also be expressed as n log 2, where log 2 is the base 2 logarithm, approximately 0.693. On the other hand, the space complexity is influenced by two key factors: the recursive call stack and the storage for the results. The recursive stack requires O log en space since the recursion depth is proportional to the logarithm of n. For result storage, we note that there are up to O2 log n combinations, and the length of each combination is proportional to the recursion depth, which means each combination takes O log n space. Therefore, the total space required for storing results becomes O2 log n asterisk log n. When we combine the space used by the recursive call stack with the space needed for storing results, the overall space complexity of the solution comes out to be O2 log n asterisk log en. This reflects the balance between the exponential growth in the number of combinations and the logarithmic depth of each. Comparing this to a brute force approach, where we might test all subsets of integers from 2 to n1 to see if their product equals n, it becomes clear how much more efficient this solution is. A naive brute force method would result in a time complexity of O2 to the power of n, which is vastly more expensive. In contrast, our approach focuses only on valid factors, avoiding unnecessary checks and leveraging recursive backtracking. By incorporating early termination using break, it prunes invalid paths efficiently, ensuring that the exploration is limited to relevant combinations. To summarize, the time complexity of this solution is O2 log n, which can also be written as O n log 2, and the space complexity is O2 log n asterisk log n. This implementation is optimized for generating factor combinations efficiently by leveraging recursive backtracking and early termination to avoid the exponential blowup seen in naive approaches. The result is a solution that balances the need for thorough exploration with computational efficiency, making it well suited for this problem. When tackling factor combinations, there are a few common mistakes to watch out for. First, many solutions fail to ensure that the factor combinations are sorted in ascending order. This is essential to avoid duplicate results and to meet the problem's constraints. To address this, you can use backtracking with a start variable to ensure factors are appended in increasing order. Another common issue is including 1 as a factor. While 1 is technically a factor of every number, it's typically excluded from valid combinations unless explicitly stated otherwise. The solution here is to start factorization from 2. Additionally, generating permutations instead of combinations, such as 2, 6, and 6, 2, can lead to duplicates. This can be fixed by always appending factors in ascending order through careful constraint enforcement in the recursive calls. Finally, inefficient recursion is another problem. Testing factors all the way up to n can lead to redundant computations. A better approach is to only test factors up to the square root of n, which significantly reduces the work involved while still ensuring all valid combinations are captured. Now, let's consider some edge cases and key insights for interviews. Edge cases like n equals 1, small primes, or n equals 2 are often mishandled. For instance, when n equals 1, there are no valid combinations, so you should return an empty list. Similarly, for prime numbers, you need to ensure that no invalid combinations are produced. Handling these cases correctly demonstrates a solid understanding of the problem. From an optimization standpoint, limiting factor checks to the square root of n is an important pattern to emphasize. It shows mathematical insight and reduces the problem space efficiently. Mastering the backtracking framework is another critical skill. You should be able to clearly articulate how constraints, like ensuring ascending order, are enforced during recursion. Additionally, discussing edge cases like small inputs and large primes is crucial in interviews. Finally, understanding the time complexity of the backtracking approach, approximately O n log n, is important, as it reflects the number of recursive calls and factorization steps involved in the process. Next, let's connect this problem to some related problems on LeetCode that share similar concepts. For example, problem 39, combination sum, uses a similar backtracking structure but focuses on finding combinations that sum to a specific target. Problem 78, subsets, is another backtracking problem, but the goal there is to generate all possible subsets of a given set. On the other hand, problems 46 and 47 deal with permutations. Problem 46 focuses on generating all permutations of a set of numbers, requiring a slightly different recursive structure compared to combinations. Problem 47 extends this by introducing duplicate elements, which means you need to handle those duplicates explicitly to avoid producing redundant results. Studying these problems can help you build a deeper understanding of backtracking and how it can be adapted to different scenarios. Finally, let's explore some alternative approaches and their trade-offs. One option is to use an iterative solution instead of recursion. This involves simulating backtracking with an explicit stack, which can be slightly more memory efficient in languages with limited recursion depth. However, implementing and debugging iterative solutions can be more challenging than recursive ones. Another approach is to use prime factorization preprocessing. By pre-computing prime factors with a sieve, you can generate combinations more efficiently, especially if there are multiple queries on the same input range. The trade-off here is that this adds pre-processing time and increases the complexity of the solution. A third option is dynamic programming, where you store previously computed factor combinations for smaller numbers to avoid redundant calculations. While this can save computation time, it increases memory usage and requires careful management of the DP table. Each of these methods has its strengths and weaknesses, so the choice depends on the specific constraints and requirements of the problem you're solving. Thank you for watching this walkthrough. To summarize, we tackled the factor combinations problem using recursion and backtracking. It's a great example of how algorithmic thinking can simplify complex problems. If you found this helpful, don't forget to like, subscribe, and check out more of our tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!